Okay, so I'm going to attempt to make at least one video, maybe multiple videos, exploring this idea that I've been exploring for a number of weeks now, which is mathematics as therapy. That's the initial idea, and I don't think that people are exploring this correctly. So, what I don't mean is mathematics as a hobby, right? So, I'm not a mathematician, nor am I a mathematics enthusiast or mathematics hobbyist. I don't participate in this whole idea of math is fun and we should get hyped up on math and so forth. Therapy is not fun. Therapy is hard, right? And mathematics, I believe, has an inherently therapeutic quality. It's the martial art of the mind, in a sense. It is and it's therefore a form of meditation and therefore can be a form of therapy. But it is terrifying, ultimately, just like confronting traumatic experiences in general is terrifying. Uh, but my conclusion increasingly is that mathematics is the way to address basically any issue that you're dealing with therapeutically in the most direct way possible. But what you have to do is not what we've done collectively as a species, which is approach mathematics by first denying the reality of a human subject being the one who's doing mathematics. In other words, we assume this sort of abstract idea that you are just sort of a floating brain observing these mathematical concepts without any existential relationship to them, and that's not true. And our assumption that that's the case has led us to extremely disastrous conclusions throughout history. Things like the nuclear bomb, things like uncontrollable machine learning, and so forth. Basically, our assumption that mathematics has nothing to do with the direct matters of human existence is just wrong. And my hope in this video series is to actually prove that, like attempt to prove that in a mathematically consistent way. The bigger idea behind the idea of mathematics as therapy is this idea of existential mathematics. In other words, something that I wish mathematical geniuses throughout history, which I am not, of course, but I wish that these people would have already nailed this down, and they haven't. And you can't really blame them in the sense that there's a lot of work to do with mathematics, right? They've done an amazing job, on one hand, of just charting the universe, which is mathematics. On the other hand, they have never gotten around to addressing what seems to be the fundamental issue, not only with mathematics, but with our, mathematics is an expression of human beings wrestling with, I believe, one central problem. So the bigger idea behind existential mathematics is what I'm ultimately aiming towards, which I'm calling radical depressive realism. For the time being, I haven't worked out everything I have to say about this, but what it's going to be is a Bayesian theory of suicide, which is, I believe, an extremely important existential issue. Camus was wrong. It's not the most fundamental question of philosophy, but according to my theory, it's, depending on how you look at it, either the second most or the third most important question of philosophy. In other words, it's up there. It's extremely important. He was on the right track in that sense. That's where this is all headed. But before we get there, we have to do some basic things. And so I decided to, as an introduction to all of this, to focus on three famous paradoxes in mathematics. I should say that there's this idea that paradoxes are different, that there are different kinds of paradoxes. I don't accept that idea. I believe basically all paradoxes that are actually paradoxes resolve into the same paradox. They're just observed in many different ways. Things that are apparently paradoxical, but we can actually resolve the paradox by going back and realizing that we made a mistake in our thinking. Well, those aren't really paradoxes, are they? Those are just mistakes. A paradox, in my view, is something that cannot be resolved despite our best efforts, and it will never be resolved. Like, as far as we can tell, there is simply no solution. That is what I mean by paradox. And three, of the most important such expressions of what I believe is the same paradox in mathematics are the Shoreline paradox, the Riemann paradox, which involves the Riemann rearrangement theorem, and Zeno. Zeno's paradox, which again, I believe there was just one paradox. He supposedly said, or he supposedly presented multiple paradoxes. I don't think that's true. I think it was just one thing. So, the Shoreline paradox. It starts with a very simple idea, which is basically Archimedes, the guy who proved this thing, a circle, right? Very simple. He gave a very beautiful proof for both the circumference, the length of the circumference of a circle and the area of a circle using calculus in something like 250 BC. Like, he was way ahead of his time. That's why he's often considered the greatest mathematician ever. He called this the method of exhaustion, but it's essentially the same thing as approaching a limit infinitely in calculus. It's the same idea. And with that idea, he proved in a very beautiful way the circumference and area of a circle. And you can look it up. He used, inscribed and containing regular polygons of basically infinitely many sides. And he had to construct this by hand because he didn't have computers or calculators. So it's an especially visually beautiful proof. But you can boil down what he was saying to something very simple, which is that this circle can be unwrapped, topologically speaking, into this triangle. And we have the Pythagorean theorem. It's a very simple, straightforward theorem, one of the most important in mathematics. And that will give us the area of this triangle and the length of this line. As soon as we perceive that we can topologically convert this into this triangle, which you could do physically with actual string, if you really didn't believe that this is true, you could prove it to yourself in reality. But once you see this, you can reduce the idea to this simple observation that these have the same area, and that the length of this bottom line of the triangle is equivalent to the circumference. So with that idea in mind, suppose you're some engineer and your boss comes in and they ask you to use that same thinking to measure the shoreline of Great Britain by the end of the day, or else you have to deal with their bullshit. So you just want to go home, you don't want to deal with your boss's shit, so you have to give an answer. The first problem you run into is that the shoreline of any landmass is dictated by the ocean, basically the depth of the ocean. And the ocean is moving. It's very complicated. And in order to give a literal answer, you would have to explain the movement, the overall movement of the ocean, which would involve turbulence and the entirety of wave theory, not just simple sine waves, but what the ocean is actually doing. And it's constantly changing, and the polar ice caps are constantly melting. So you can't, you might conclude. But your boss is going to want something, so what if we take a satellite photo of Britain and we collapse this issue to a two-dimensional snapshot? That will at least, that will limit the problem to one moment in time, and you can give a rough estimate at the very least of what, I can give you the exact length of Great Britain at one time, right? He might be satisfied with that. Your asshole boss, I mean. And so you want to use this same idea. You want to unfold the overall perimeter of Great Britain into a line and measure that line. Simple. But the issue with this proof, of course, is, the length of this line is 2 pi r. R is what? The radius. What is the unit of the radius? Well, that's an arbitrary decision. It could be inches, millimeters, something else. In other words, it has to be referred to something that's humanly observable to make any sense. If you're an engineer in America, it's probably inches. So, okay, we'll choose inches. But you could choose any unit. You could say that, when I unfold Great Britain's shoreline, it's equivalent to 1 Great Britain's shoreline. Right? So when your boss comes in, okay, how long is it? You say 1. It's 1 shoreline long. He's not going to like that. He wants more specificity, right? So we choose inches, let's say. Well, you can do that, right? You can unfold it, and you can measure it in inches, and you'll have an answer. However, mathematicians notice that because your decision is arbitrary, you could choose any unit, right? So what if you chose half an inch? Well, your overall answer would be twice as long. But that seems obvious, right? Like half an inch is half of an inch, so that's not surprising. If you chose a quarter of an inch, your overall answer would be 4 times as long. Again, not too surprising. The problem is that you can continue this process infinitely to a limit of 0, meaning using the same calculus that we used, that is true, that it will approach, as you infinitely choose a smaller and smaller ruler, it'll approach a finite limit of 0. And in fact, what I just described, 1/2, 1/4, 1/8, 1/16, 1/32, that's Zeno's paradox. So Zeno's paradox is also the Shoreline paradox. Zeno's point was about like crossing the room or an arrow being shot at a target, but it's the same observation, which is that as you approach a limit of 0, which is to say, as you finish doing what you're doing, the output, paradoxically, the length of the shoreline, goes to infinity, right? Positive infinity. So in some real sense, if you use a ruler of length 0, the length of the shoreline is infinite. How is that possible? How can a shoreline be infinite? Right? We intuitively assume it's a finite thing. Well, mathematically, it is, right? And there's no way around this. So, Riemann's paradox, Riemann's rearrangement theorem, is essentially the same thing, but with regards to infinite series in general. So not just convergent series, but divergent series. And the gist of it is that you can interpret these differently with different grouping orders, and things that you would think would have the same result due to intuitive assumptions of associativity and commutativity and axiomatic assumptions that we use in arithmetic ordinarily, especially in like elementary level math. You would think that you would get the same result, but no, when you're dealing with infinity, you get infinitely many different results. And in fact, there are 3 forms that you can group the results into. You either get infinitely many results, or you get the same result no matter what you do, or there is no sum no matter what you do. Right? So all of these paradoxes, everything I'm going to talk about, in fact, not only in this video, but in the overall theory, has to do with the concept of 0, 1, infinity. And instances where those 3 things, which should be different things, you would think, appear to be the same thing. Right? And that's upsetting to us psychologically. And I have a lot to say about that, but I'm going to try to represent this as simply as possible by using a square, and we'll eventually get back over to this circle, because those are the 2 most intuitive geometric objects, right? Every kindergartner knows these. So I'm going to start with a unit square, and I'm going to say, okay, that has an area of 1. But let's say, we refer to the center line of this circle, or this square, and we rotate it 180 degrees, and we fill in the space that the square covers. Well, that's going to imply a cylinder, right? You could generate a cylinder in that way. So the cylinder will have 1/2, radius of 1/2. It'll be height 1, and so forth. So the volume of this will be equivalent to pi/4. And it might seem like, wait a minute, that's less than 1. But this is cubic units. We have to remember these are cubic units, and this is square units. So this is referring to a cube, which we could unfold into a 2-dimensional cross side lengths of cube root of pi/4. And that equals, roughly 5.1075. That's greater than 1. Okay, that makes sense. But what if we cut the square and we rearranged it, hint, hint, Riemann's rearrangement paradox. We rearranged it into a rectangle instead. So we've cut it in half. So one length is half, and the combination of the other is 2. So this is half as long as the side, this is twice as long. The area is still 1. Great. So let's do that same operation of rotating at 180 degrees. We now get a wider and shorter cylinder, right? And this has a volume of pi over 2, so that's bigger. So this might seem a little more troubling because our area has remained the same, but our volume has gotten bigger. Strange, right? So if we continue this process, we get a disk, something that's approaching a coin. This volume is even bigger. It's pi. And the point is you could continue this process infinitely, of course, and this side length will collapse to 0, and this will extend to infinity. But the area, somehow, throughout this whole process, will remain 1. Interesting. Whereas the volume of our coin, our cookie here, will be infinite. And also, the side length or the height of the coin will collapse to 0 as well. So both of these things will eventually, in one sense, be nothing, in another sense, be infinite, and in another sense, remain 1. Strange, right? Well, like if you had like pre-calc in high school and you can remember the idea of a limit, this is just the quick rundown of that. You're dealing with the limit of 0, the limit of positive and negative infinity, depending on how you interpret it, the limit of 1, 0, infinity, etc. But you could see, like, everything I just said is mathematically true. This might seem like bullshit. It's not. This is consistent, and you can't escape these notions of 0, 1, and infinity all at the same time. We want those to be neatly delineated different things, and they're not. So going over here, like, what if we choose, just for, the sake of presentation, a different axis around which to rotate the square? Area is still 1. We rotate it this way. That gives us a top, however you want to describe it, a double cone. Volume pi times square root of 2 over 6. We could arrange it this way by putting it into a triangle, an isosceles triangle, I guess. Area also 1, but volume of pi over 3. It's getting a little bigger. Well, what if we do the same thing that we did before in diminishing one side by a half and elongating the other, maintaining the area, right? Well, you get a more complicated shape, which I rearranged into this. These are equivalent, topologically speaking, like these are the same thing, just to make it clear. So it's a double cone, but the bottom cone is getting smaller as we continue this process, and the top cone is getting taller, and the radius is getting skinnier. So essentially, as this collapses to 0 now, and this side length extends infinitely, so too will this bottom cone collapse to 0 as the radius is collapsing to 0, but this height will extend to infinity. So they're both collapsing to a point and to an infinite line that extends from that point at the same time. However, again, somehow the area remains 1 the whole time, and the volume gets small. There's a lot of trigonometry, but it's a simple idea here. I'm just demonstrating that this process continues. So the area is always 1, yet advances to a point 0, while also collapsing to a line of infinite length, infinity, which includes both the point and I was supposed to say the line, I guess. Pretty much the same idea, in other words. But, okay, let's look at circles. Right? Maybe there's something else going on with circles. So I already explained that you can unwrap this circle into this triangle. Very beautiful, interesting idea in itself. I kind of just think this is the most interesting thing in math. It gets more complicated than this, of course, but this is pretty interesting. With the same thinking, we could extend this into a 3-dimensional object, and we could unwrap a cylinder into a ramp. So these have the same area, that was Archimedes' point, and these have the same volume. Cool. So what about a cone? Again, we have a circle as the base idea, and then we have a triangular 3-dimensional concept, of a cone. What if we go unwrap that into, what would it be? Well, it'd be a right triangle pyramid. There might be some other technical name for this, but, and I drew this just to explain that 4 of these make a rectangular solid. So we know the volume of a cone is 1/3 pi r squared times the height, but the volume of this pyramid is 1/4 pi r squared height. So we have a smaller volume. In other words, we unwrapped this with this volume, and it has a smaller volume when we unwrap it. But they have the same limit, right? Like as this gets smaller, in other words, if we assign 1 to either the radius value or the height, as either of the other variables approaches 0, the overall limit will also be 0. And that's the same for both of them. So no paradox, right? Like we have equivalence. Well, so this is Archimedes' proof of the volume of a sphere. So let's go from a circle to a three-dimensional circle, if you will, a sphere. This might look complicated, but all he's saying is that this plus this equals this. So Archimedes sat in a bathtub, and he noticed that the water rose a certain amount, and he asked, wait, what is that amount? Well, it's the amount of the volume of my body that's displacing the water. Eureka, right? He figured out volume, how to measure volume. So we assume that Archimedes put a cylinder into some water and measured the line that the water rose to. And then he could literally prove that if I have a specific sphere and a specific double cone or hourglass that are, the same height and the same radius as that cylinder, those will equal the same volume. So he proved the volume of a sphere, 4/3 pi r cubed. Again, cool. Like that's a beautiful proof. But if we take his idea from the circle and apply it to a sphere, right? In other words, if we unwrap a sphere into a triangular object, what do we get? Well, we get a half cone. This is troubling and interesting. Why? Well, this sphere can be looked at as basically an infinite set of circles, in some sense. And all of those circles, as we observed, can be unfolded into a right triangle. So you could imagine that you have a infinitesimal coin, a disc, that's at the center of this. And you could rotate that disc 180 degrees, and that would imply this half cone. And you could unfold that into a triangle. You could also, in other words, do the process by infinitely many circles that are unfolded into infinitely many triangles. And each one of those triangles will have the same area as the circle that it was unfolded from, and vice versa. You could collapse the triangle back into the sphere. But as you see, we have this same issue. These are different volumes. So the half cone will have a larger volume than the sphere, which means all the paradoxes that we just observed are also the case in this relationship where, again, as you infinitely approach a certain limit with regards to one shape, the other is not aligned. So what this means is, at some point in collapsing the sphere to nothing, the sphere has become nothing, right? It reaches that limit. That's what calculus tells us. But at the same rate, this cone is also getting smaller, and you can, as we said, at every step of this process, collapse the every triangle that's implied by this into every circle that's implied by the sphere. However, at some point there's no sphere for you to collapse this into. It's gone. It's already nothing. It's reached 0 before you have reached 0 with the volume of your half cone here. So how does that work, right? Like how can this be true, and yet at some point in the process of infinitely approaching a limit of 0, there's no more sphere for this to collapse into. Right? And there's no solution to that. In other words, everything we've said here is mathematically true. There is no mistake in our reasoning, and yet we arrive at this bothersome result, which is at some point what we thought was true isn't true, except it is, right? Okay, so that's all I wanted to cover in this initial video, is just basically the idea of paradox. I think that these are the three examples that most exemplify the core idea of a paradox. There are plenty more examples. There are infinitely many, in fact. But I wanted to present them in this way, firstly because a circle and a square are very simple objects that, most people can understand. Secondly, because if you went through high school mathematics, everything I just said technically was taught to you, right? Like, you technically learned all the math that's required to understand this. But I can almost guarantee that nobody talked about this in this way, right? You would have to be a college level mathematician, it seems, to like get anyone to take this seriously. Secondly, even if you are a college level mathematician, even if you are like Terence Tao, you're like the greatest mathematician in the world, it doesn't seem like anybody is actually applying this to the existential concerns of like the fact that we know that we're dying and that our brains are designed to try to go on living forever. Right? In other words, the paradox of the infinite as it pertains to the inescapability of the finite, and vice versa. The closest example to this is David Foster Wallace in his book Everything and More, which is about infinity specifically. But again, as I just said, infinity is only one part of the puzzle. You have to talk about the finite, and he really only addresses the finite with regards to the fact that Gerrit Cantor became more mentally ill as he contemplated the infinite. In other words, as he was giving the most compelling theory of the infinite at the end of the 19th century. Gerrit Cantor is the father of set theory, and he has an argument that's every bit as beautiful as Archimedes, for it's called the diagonal argument for what he called the transfinite numbers. What he's proving is that there are different cardinalities between infinities, specifically the infinity of the infinite set of the natural numbers and the infinity of the infinite set of the real numbers. And once you that might sound complicated, but once you understand what he's talking about, it's actually very simple and obvious. But even to mathematicians of his time, it wasn't, and they just laughed at him and said, "This is ridiculous. We want this to go away. We don't like this. It makes our brain hurt," and so forth. And long story short, it didn't go away, of course. In fact, became an essential feature of mathematics, and also contemporary physics has only demonstrated that all of these paradoxical things are inescapable, essentially. And they're inescapable. In other words, if you want to describe nature, you have to involve things that we don't like irrational numbers. Hippasus was supposedly thrown into the ocean by Pythagoreans who could not accept the constructibility of irrational numbers according to the Pythagorean theorem, right? They just had a hard time accepting that truth. You can't do without that. You can't do without negative numbers, which we'll get into more, I hope. Complex numbers and hypercomplex numbers and the transfinite numbers when you get to Cantor. All of these things are inevitably paradoxical, and also you need them to describe what is actually going on in physics. And there is no resolution for any of these problems. In other words, they are all mathematically consistent. If you think, 1, 2, 3 is real, then you think all of this is real, essentially. So sure, if you want to not count, you can throw out all of mathematics. And I'm not convinced that that's necessarily a bad idea. There are people who have a physiological condition called annumeracy, meaning they could be perfectly capable cognitively in all, any number of ways, but they cannot count. They don't understand what counting is. They're essentially colorblind with regards to numbers, which is very interesting. And it suggests that, our ancestors, if you go back to prehistory, didn't have math textbooks. They didn't have math teachers. Nobody taught them how to count. So how did they learn? Well, it was obviously an intuition that eventually emerged over a long, 4 billion years, essentially. But if you were to, if we were able to study the brains of prehistoric ancestors, I'm pretty sure we would see some physiological feature that corresponds in the brain to the ability to count. I don't know what that is, that's a cognitive science question, but some people don't have that, and it's clear that their brain is functioning perfectly fine in other regards, but they just don't have that. Just like someone who's colorblind or someone who has facial recognition deficiencies and so forth. something specific is off in their brain, they're not stupid, right? And in fact, the concept of stupidity turns out to itself be a paradoxically stupid idea. So anyway, the intuition to count is, in a sense, the existential problem that we have with mathematics. And the overall approach to mathematics, which is existential mathematics, for one, would reintroduce the human subject into the actual math. Like, we don't want to do that because we think that will mean, people